How do we keep billions of devices across the internet all synchronized to each other? All the way from banking to checking HTTPS certificates to making sure your alarm goes off at the correct time in the morning. We need all our computers to have the right time. And this is where the network time protocol comes in. It gives us a way to synchronize computers all across the world to a pretty accurate level. We're going to have a look at how this algorithm works and what accuracy we can expect from it. And at the end, we'll have a bit of a look at what we can do to improve on it. So we'll start with an overview of the basic structure across the network. NTP works by having a hierarchy of servers with reference clocks at the top, connected to primary servers, and clients towards the bottom. We group these servers into levels which are called strata, which basically represent how many hops away from a reference clock we are. And the arrows in this diagram represent the flow of the time signal from the reference clocks at the root, synchronizing down towards the tree. And as we can see, they always go from top to bottom and within the same level, but we never synchronize to someone further away from a reference clock than we are. And the reason we synchronize within the same level is so that we can just get a bit more better reliability. And there are several reasons why we have this hierarchy. One, it allows the massive scale that we need across the internet, where we have probably billions of devices nowadays that all need to be synchronized. And we don't want to overload the primary servers with millions of these requests, so we delegate it to secondary servers and so on down the hierarchy. And it also prevents cyclic dependencies, where servers would be synchronizing to each other in a loop and might get synchronized to each other, but not to the actual real time. One thing we might be wondering is, how do we know what servers exist to sync to? And the answer is that public lists of these servers exist, and also nowadays there's automatic discovery servers where you connect to a central server and that chooses a few random NTP servers from across the country and returns them to the client. And that often rotates the order of the servers as well between different clients to help balance the load on the network. Before we discuss the actual algorithm, let's take a moment to look at what assumptions we're making. We're going to assume that delay across the network is symmetric, because we don't really have a way of working out what the individual request and response delays are without having synchronized clocks in the first place. And if we do have an asymmetric delay, then this is going to give us systematic errors in our calculations, but there's not much we can do about that without knowing what they are beforehand. We're also going to assume that our time servers are spread out across the internet, so there's going to be variable latencies, and there's going to be network jitter, which adds variability between different samples to the same server. We also can't trust servers to be reliable or accurate. There may be some that are just unreliably synchronized, or there could be some that are actively malicious. So we're going to have to account for these factors in our algorithms. One thing to note as well is that we use UTC for NTP, so anything like time zones is going to be handled by the operating system on top of that. Okay, so let's have a look at an overview of the different stages of our algorithm. We start by polling multiple different servers at a variable interval, which is designed to maximize the accuracy whilst minimizing the network traffic. The default values are 64 seconds on startup, and then when our synchronization has stabilized a bit, that would go up to 1,024 seconds, which is about 17 minutes. But this can be configured as well when we're running it. And at this stage, we do some sanity checks on the packets, like checking for duplicates or for these synchronization loops, or any other kind of invalid packets we'll just discard. And for each packet, we're going to calculate the offset and the delay to that server, which we'll go into next. These values are then passed through a suite of filtering algorithms where we can see that at each stage, the number of valid samples is getting filtered down and decreasing until at the end we're left with a single value, which is going to be our best estimate clock offset. And that offset is then passed to the clock discipline algorithm, which is what's actually adjusting our system clock. And that then feeds back around to the start to form a feedback loop of doing these updates. So how do we calculate these delay and offset values given a request message to the server and a response message back? Well, we're going to record these 4 timestamps on sending and receiving, and the delay we're calculating is just the entire round trip minus the time it's spent processing on the server. So just the length of the two arrows here. And we can see again that we're assuming that the delay is symmetric here, which is why it's delta over 2 on each of the arrows. To calculate the offset, that's going to be the difference theta here on the right, where t0 is the same timestamp on both computers, and this is the offset that we're trying to minimize with this algorithm. And we can measure this by looking at the request and the response message. So for example, for the request message, we take the send timestamp, add on the delay and the offset, and that should give us the receive timestamp, and the same for the response, apart from we subtract the offset this time. And then solving those simultaneously gives us a value for the offset. So we have an equation for the delay and the offset that we can use, and we can calculate these numerically for each packet that we get continually over time and for multiple servers. So we take all these samples and we put them into the clock filter algorithm. This is taking these samples over time for each server and is going to give us a single sample per server, and it's also going to tell us which servers are selectable. Basically, which ones have good enough accuracy to be continue used in the next stages of the algorithm, and which ones we're just going to be dropping at this stage. So the way this works is by using an 8-stage shift register for each server and putting new samples into one end of this, and then our value for the server is just going to be the best sample from this shift register. So what do we mean by the best sample? By best sample, we mean the sample with the lowest delay, which is because statistically, the samples with the lowest delay are likely to have the most accurate offset, and it's the offset that we care about. So as a bit of motivation for why the lowest delay gives us this is a plot of the delay versus the offset for lots of samples to the same server, and what we can see is that as the delay increases, the variation in the offset also increases. So if we have a sample with a lower delay, the variation in the offset is less, so the sample is likely to be more accurate. And at least partly this is because with a lower delay, there's less chance for asymmetry between the request and the response message. So we're getting new samples, and each time we're keeping the lowest delay sample selected, and then if we get a new message that has a lower delay, that'll become the one selected. And one thing we can notice is that by doing this shifting, eventually the old samples are going to drop out of the end of the shift register, which means that we're always going to be moving on to new data, which helps keep us up to date. And this gives us pretty good results. So the graph is not terribly clear, but the one on the left we can see has a lot of noise, and that's the one before doing any filtering. And the one on the right is after we've done this filtering. So we can see it's done a pretty good job at filtering out the noise in the offset values. We can also see, or you can see slightly if you look at it closely, that it is quite boxy, that the filtered one on the right, and that's because of using this shift register, where we only select a new sample when either a better one arrives or the current one gets shifted out. So we can end up holding onto the same sample for multiple cycles. Okay, so we've got a single sample per server. And now we need to also decide which servers are selectable. And to do this, we start by calculating the dispersion for each sample. And that's a measure of the error bounds of what the actual offset could be due to the client's and server's clocks skewing apart over time. And we calculate that as the sum of the precisions of the server and the client, where we define the precision to mean the latency of reading the system clock. In modern machines, that's somewhere around 100 to 1,000 nanoseconds. The server precision we get sent to us from the upstream packets. And we increase this by 15 microseconds every second because over time the clocks could drift further apart because of that clock skew, so our error bounds have to increase to represent what the maximum error could be. So we do that for each of our 8 samples in the shift register, and we're now going to combine that into an overall peer dispersion for this server as a whole. And that is just the weighted sum of the individual dispersion values. And to calculate these weights, we number the samples 1 to 8, with 1 being the newest sample, 8 being the oldest, and then we weight the dispersions by 2 to the minus I. So the most recent sample will have a weight of a half, then a quarter, etc. And that just means that we're going to favor newer samples. So if the accuracy of the server changes, then we want to know about it pretty soon so we can pull from different servers or whatever we're going to do to handle that case. Okay, and then we combine this value with the delay that we've calculated and also with the delay and the dispersion that we've got from the upstream server. And combining that gives us a route distance for this server. And we represent that by lambda. And that's a measure of the maximum error of this source. And this is what we use to determine whether a server is selectable. We compare it to a threshold called the select threshold. And if the route distance is less than the threshold, then the server is selectable and it will carry on to the next stage. And otherwise, we discard it at this stage. And this is basically filtering out any servers that just have really massive error bounds. One other thing that we're going to need to calculate at this stage is called peer jitter. And this is basically a measure of the variation between samples from the same server. So we calculate that as the root mean square of differences between the offset that we have selected and all the other offsets in the shift register. And that's just a measure of how spread out different samples to the same server are. We need to calculate that at this stage because we need to have all the samples from the server available to us, but we're going to come back to this later. Okay, so that's the first stage of the algorithm done. Let's take a step back and see where we've got to. We've taken samples over time for each source, chosen the best sample for each source, and selected which sources are good enough to use. And for each source, we've calculated the offset and the delay, the route distance, which is a measure of the maximum error, and the peer jitter, which is a measure of the variability of that source. So the next stage of the algorithm is called the clock select algorithm, which takes this set of selectable samples and filters out any samples that are giving us the wrong time. So we're going to define a piece of terminology. We're going to call true chimers the servers that have the correct time, and false tickers the ones that have the wrong time. It could either be that these are inaccurately synchronized, or they could be actively malicious, but either way, we're going to filter them out at this stage. The way we do this is by defining a correctness interval for each source, which we define as the measured offset plus or minus the route distance. And what we say is the true value of the offset is going to be somewhere within this interval. And this interval is going to be bigger for samples that have a larger route distance, so ones that have bigger error bounds, and smaller for ones that have smaller error bounds. So we say the true value is going to be somewhere in this interval. And we do this for each of our sources, and we want to find the biggest overlap between them, which we call the intersection interval, the smallest interval which overlaps the biggest number of these correctness intervals. And then we label all the sources that are in the intersection interval as our set of true chimers. So let's have a look at a diagram for this. Here we have 4 different servers that we're polling from, and each of them has a measured offset value and a route distance, which gives us a correctness interval for each of the sources. And the intersection interval is going to be this point here, where 3 of our servers are overlapping, and we can see that that's the maximum amount that are overlapping at any one time. And then all the sources in this intersection interval are the true chimers, and the one outside it is a false ticker. And one thing to notice is that inside this top sample, the actual measured value, which is this line here, is actually outside of the intersection interval, but we still count it as a true chimer because the correctness interval as a whole overlaps the intersection interval, so the true value could be inside the intersection interval. So how do we actually find this interval given a set of correctness intervals where we want to find the maximum number overlapping? So we do this by an iterative algorithm where we're going to start by assuming that there are no false tickers, and we're going to try and find an overlap where 4 of our servers have overlapping intervals. So we're going to label the number of overlapping intervals at each vertical section, and then we're going to scan this from left to right to try and find a point where the number of overlapping samples is equal to the number of true chimers that we're looking for. And so we're going to try and find a lower bound by scanning left to right. Here we've got to the end without finding 4 overlapping intervals, so we're just going to set a lower bound marker where we end up. And we're going to do the same thing, scanning from right to left to try and find an upper bound. And again, we see that we haven't found one in this case, so we set a marker where we end up. And at the end of each round, we're going to see, is the lower bound marker less than the upper bound marker? Have we got a valid intersection interval? So in this round, we haven't, so we're going to do another iterative pass over these. And this time, we're going to increase the number of false tickers, so we're going to try and find an overlap of 3 samples this time. So again, we're going to scan from left to right, and then this time, we're going to get to this point in the middle. We see, the number of true chimers is equal to the number that we have overlapping at this point, so we're going to set our lower bound marker at the point where we went from 2 to 3. We're then going to scan from right to left to find where the upper bound is, and again, we're going to get to this point in the middle where we found the value we're looking for, so we set our upper bound marker to be there. Then we do our check again. Is this a valid intersection interval? And in this case, this is a valid intersection interval. So we've found the 3 true chimers and 1 false ticket. So at the end, we would just do one more linear pass over to see which of our intervals is actually falling inside the intersection interval that we found. So now we have a set of samples that are more or less telling the right time. The cluster algorithm now is going to take these and look at the jitter between them and give us a set of samples that are all closely clustered together. And this is where we're going to use the peer jitter that we defined earlier. So as a reminder, this was a measure of the variability between different samples within the same source. And we're now going to define something called the select jitter, which is a measure of the variability between the different sources that we have left. So we start by defining this metric d between 2 samples I and j, which is the difference between their offsets multiplied by the root distance of I. And then the select jitter for a candidate I is the root mean square of this metric d to all the other candidates j. And this is just a measure of how far candidate I is from all of the other candidates. And the root distance term just means that we favor samples with lower root distances, i.e. that have a lower maximum error. So we have peer jitter, which is variability within the same source, and then select jitter, which is variability between different sources. So that all sounds a little bit confusing. So let's have a look at a diagram to see how we use this. So the blue circles here are going to represent our different sources that we have, and it's going to represent the peer jitter of each of them, which is the variability within that same source, and the bigger the circle, the bigger the variability of that source. And the distance between the circles here is going to represent the variation between the different sources. So we can see that sample 1 has a value that's quite far away from the other values, and the other values all quite closely clustered together. And we're then also going to plot the maximum of the select jitters as a green circle. We'll only plot the maximum because that's the only one that we actually care about, and otherwise our diagram would get quite confusing. So in this one, this is the select jitter for sample 1, which is the furthest away from all the other candidates, and we can see it's a pretty big circle because the select jitter of sample 1 is quite big. It's quite far away from the other candidates. And so what we do is we again do this iteratively, and we prune that candidate that has the biggest select jitter. So we're going to discard candidate 1 here, and then we recalculate the select jitters of the remaining ones, and that leaves us with the diagram on the right, where we have the same 3 sources left minus sample 1, and the green circle here is the one for sample 3, and that's pretty small because it's quite close to all the other samples. And so we do this iteratively, and we iteratively remove the worst true chimer from the group, the one with the highest select jitter. And we have two conditions for termination. Either the number of survivors that we get left with is less than some threshold, which is by default 3. And the other condition is when the maximum of the select jitters is less than the minimum peer jitter. So that means that the variation between each of the sources is smaller than the variation within each source. So there's not much point continuing because the error of each source outweighs the error between the sources. So this leaves us with a small handful of survivors. And this brings us to the last stage of our algorithm, where we're going to combine those last few survivors into a single offset value. And we combine these by taking the weighted average of these offsets, which is weighted by the reciprocal of the root distance. Again, because the root distance is a measure of the maximum error, so taking the reciprocal of that is going to favor survivors with the smallest distance, so the smallest maximum error. And that gives us the single combined clock offset that we can use to adjust our system clock. So how do we adjust our system clock? We have several cases. If our clock offset is small, then we're going to slew our clock, which means we slightly adjust the clock oscillator's frequency by a small amount, either faster or slower, so that over time our clock is going to converge to the true time. And this is going to preserve the fact that the clock will be monotonically increasing, because we don't want it to be jumping about all the time when we're setting the clock, because that's going to wreak havoc for things like actually timing things on the device. If the clock offset is bigger, however, we are going to directly step the clock to the correct value, because it would take a long time to slew it gradually. Usually this will only happen when we first start up the process, because our clock might have drifted while our computer was powered off, so we need to correct for that offset when we start up the process. But if this does happen while we're operating normally, then we're going to wait for a certain interval to make sure that we actually want to do this, and it's not just an anomaly in our calculations. And if we do have a really massive offset, then NTP basically throws its hands up in the air and gives up, because something out of its control has gone wrong. Either a human has come along and changed the system time to some random value, that's their own problem in that case, or the system timekeeping is broken, or something else very wrong has happened, so we can't really fix that with NTP. So NTP just terminates at that point. But in general use, this isn't going to happen. There are a few other mitigation algorithms that NTP uses that we're not going to go into here. For example, there's an algorithm for when we're polling from multiple servers with very low delay, such as on a fast LAN, where there can be jitter due to just differences in the servers, and we don't want to jump between them, so the algorithm can help prevent that. And there's also a mechanism for setting a preferred peer when we have both a high accuracy and a low accuracy source connected to the same computer, and we don't want to dilute the high accuracy value with the low accuracy ones, which would make things worse. So what accuracy can we expect from this algorithm? NTP on the public internet can sync to within tens of milliseconds. Depending on what the network conditions are, it might be as good as a few milliseconds, which is pretty good over the massive internet with random delays on it. If we're on a fast LAN, such as in a big data center that has its own time server, that could be less than a millisecond of delay. But if we do have these asymmetric delays, then errors can be on the order of 100 milliseconds or worse. The accuracy will depend on how often we update from upstream. So as an example, if we update every 15 minutes, that could give us an accuracy of about a few milliseconds, whereas updating every minute can give a millisecond or even less. But this is, again, a trade-off between the load on the network against the accuracy we can expect. So there's a bit of a balancing act there. And we can also get a higher accuracy if the algorithm is implemented directly in the operating system kernel, which might be the case now for modern operating systems, rather than in software, because that can give us faster hardware timestamps rather than software timestamps that need to wait for operating system delays. So this is fine for general use. You know, humans aren't going to be able to tell if the clock is a few milliseconds off, but for some applications, we do need better accuracy. So we're going to look at two ways that we can get a better accuracy than this. One of these is the precision time protocol, which can give us sub-microsecond accuracy. So this is used on things like cell towers, where they need to synchronize very precisely for the phase offset as well, I think. And this does use hardware timestamps to avoid those operating system delays. And it also uses a slightly different architecture to NTP, where we have master nodes and all the other nodes being followers, and the master node will broadcast out the time information to all the followers, rather than in NTP, where the clients will poll the servers periodically at their own intervals. In this one, the master broadcasts to all the follower servers at the same time, and then there's a similar exchange of messages, like in NTP, to calculate the delay and the offset. Masters can also send what are called follow-up messages, which contain a more accurate timestamp for the message that they just sent. And that may seem slightly counterintuitive, but that's basically because some network equipment, you can only get an accurate send timestamp once we've actually sent the message. So we're going to send a message on after we've sent the message with the more accurate timestamp, so the follower can do its more accurate calculations. And there's also a mechanism called transparent clock, where network equipment along the way can modify PTP packets to correct the timestamps for the delay in traversing the network. So a switch that's en route between the master and follower could modify a PTP packet to effectively say, this packet spent 10 milliseconds processing on this node, so account for that in your calculations. And that's going to give us a better accuracy than in NTP. And finally, we also have the White Rabbit system, which is an Ethernet-based network, which is used at places like CERN for their control systems. And using Ethernet allows this to be flexible and modular, and is pretty simple to configure and maintain, and it provides robustness against packet loss as well. And this can give us sub-nanosecond accuracy, which is needed for things like at CERN, where they're controlling the Large Hadron Collider, where they need to be super precise in the timing of controlling their equipment. And this uses what's called synchronous Ethernet to achieve synchronization. And that is subtly different from synchronization. Synchronization is only synchronizing the frequencies of the clocks, but not necessarily the value of the clock. And we do this by encoding the clock frequency with the data that we send down the Ethernet, and the receiver can then recover the clock signal from that and set its clock frequency to that. And then on top of that, we use PTP to synchronize the actual time value. So we're synchronizing the frequency and the value separately, which can give us a higher accuracy. Okay, so that's two ways we can get a higher accuracy than NTP. To summarize, I'll go back to the overview slides that we saw at the start. So we've seen how we poll multiple different servers to get an offset and delay sample for each one. The clock filter algorithm chooses the best sample for each server and determines which servers are selectable. The clock select algorithm determines which sources are true chimers and which are false tickers. The clock cluster algorithm trims the set of true chimers down to a set that's closely clustered together. And then the clock combine algorithm combines these into a single offset value, which we then use to adjust our system clock. Okay, so that's been a tour of the NTP algorithm. Thank you very much.